In this section, I'm going to be considering Fourier series and their relationship to linear time invariant systems. We'll revisit the eigenfunction properties of LTI systems and see how these properties can be exploited in conjunction with Fourier series in order to more easily solve problems involving LTI systems. Recall that earlier in the course we saw that complex exponential functions are eigenfunctions of linear time invariant systems. And in particular, what we saw was that for an LTI system denoted by script h with the impulse response little h, a relationship of this particular form is satisfied, where the function denoted by h subscript L is given by this integral here. In other words, what we have, if we look at this relationship here in more detail, it's saying that if we take a function of the form e to the st, where s is a constant, in other words a complex exponential function, and put this into the system denoted by script h, the output that we get is the same complex exponential function e to the st multiplied by a constant that depends on s, where this particular constant is given by this function here, which is defined by this integral, which is known as a Laplace transform integral. Now, since complex exponential functions include complex sinusoidal functions as a special case, this particular result here carries over to the case of complex sinusoidal functions. In other words, we can take this highlighted relationship here and substitute j omega for s. In other words, consider the special case of complex sinusoids, and this gives us the pair of equations that's shown here. So in some sense, these equations here are nothing new. We're just considering the special case of complex sinusoids rather than the more general case of complex exponential functions. So essentially what we have is for an LTI system that's denoted by script h with the impulse response little h, this relationship here is satisfied, where the function capital H is given by this particular equation here. And if we look at what this relationship is saying, it's saying that if we put a complex sinusoidal function into the system h, in other words a function of the form e to the j omega t, where omega is a constant, the output of the system is simply the same complex sinusoid multiplied by a constant that depends on omega, where this constant is given by the function capital H, in other words given by this particular function here. And I should point out that the integral that appears on the right hand side of this equation, this integral is of great significance. It's referred to as a Fourier transform integral, and we'll be looking at the Fourier transform in great detail later in the course, but this is the first point in the math where the Fourier transform starts to creep in. Now observe that the quantity h of omega is quite important, because h of omega corresponds to the eigenvalue that goes with the eigenfunction e to the j omega t. So for this reason, the function capital H is quite important, because this function is the function that allows us to determine eigenvalues. And because this function capital H is quite important, we give it a special name. We refer to it as the frequency response of the system. At this point, I'd like to consider how we can use Fourier series in conjunction with the eigenfunction properties of LTI systems in order to more easily solve problems involving LTI systems. So suppose that we have an LTI system with input x, output y, and frequency response function capital H. And suppose that the input to the system x is t-periodic and can be represented using a Fourier series, in other words a summation of this particular form here. Then using our knowledge of eigenfunctions of LTI systems, we can conclude that the output of the system, which is denoted by y, is given by this particular formula here. And if you compare this formula here to the formula for the input to the system, you can see that the only difference between them is that we've added this multiplicative factor h of k omega naught. And this corresponds to the eigenvalue that goes with the eigenfunction e to the j k omega naught t. So here we're using the eigenfunction properties of LTI systems in order to find the output of the system given its input. And the determination of the output simply involves the operation of multiplying by a constant. Perhaps what's more important to note here is what we're not doing. In particular, we're not computing a convolution. In effect, we've found a way to exploit eigenfunctions in order to find the output of an LTI system given its input in a way that doesn't require convolution. In other words, by using eigenfunctions, we've transformed a problem that would normally involve convolution into one that simply involves multiplication by a constant. And clearly this is highly beneficial, since multiplying by a constant is much simpler than computing a convolution. At this point, I'd like to consider an example to illustrate how we might make use of the result presented on this slide. And in particular, I'd like to consider example 5.9. In this example, we're given an LTI system with the frequency response function h, where h is given by this particular formula here, and we're asked to find the response y of the system to the input x, where x is given by this particular formula here. And the idea behind this example is we want to use eigenfunctions to help solve this particular problem. So in order to do this, what we need to do is rewrite the function x, in other words the input to the system, as a weighted sum of complex sinusoidal functions. In other words, write it as a Fourier series. So to do this, what we want to do is take the cosine function and use Euler's relationship to rewrite it as a pair of complex sinusoidal terms. So in other words, we can use this particular relationship here to rewrite the cosine function as a pair of complex sinusoidal terms. And this gives us this next line here. And this line is essentially a Fourier series with two non-zero terms. So we can more formally write this as a Fourier series, which is what's shown on the next line, where omega naught is equal to 2 pi. So that's what this particular constant is equal to. And the Fourier series coefficients, there's only two of them that are non-zero. In other words, there's two ck values that are non-zero, particularly for the values of k equal to -1 and +1. And in both cases, these coefficients are equal to 1/4. So now we have a Fourier series representation for the input. To find the output of the system, y, all we need to do is take the Fourier series that we have for the input, and each of these terms we need to multiply by the eigenvalue that goes with the eigenfunction e to the jk omega naught t. In other words, we need to insert this multiplicative factor, h of k omega naught, into the formula. So this gives us the output of the system, and all we need to do is just evaluate this Fourier series summation. So the first thing we can do is we can expand out this summation in terms of the two non-zero terms that we have. This gives us the next line here. And then we can substitute the values of c of -1, c of 1, and omega naught, which gives us this next line here. And then we need to evaluate the function h. H is being evaluated at the point -2 pi and also at the point 2 pi. And we can do this very easily by using the formula that's given for capital H up above here. So we can evaluate that function, and that gives us this next line here. And then what we can do next is combine the exponential functions that we have in order to get this next line, and then we can write this as a cosine function using Euler relationships, which gives us this next line here. And then just through very simple manipulations we can get to this into the form of the right hand side on this last line. So now we have a formula for the system output y, which is given by this particular expression here. And essentially this is what we were asked to find in this particular example. Now, one important observation to make about our approach to this example is that it didn't involve convolution. In fact, our approach simply involved multiplication by a constant. And what I mean by this is the following. Essentially, our starting point for this example is we had our input, in other words, the input to the system, expressed in terms of a Fourier series. And then our answer for the output was also a Fourier series, which was given by this expression. And if you compare these two expressions, in other words, this highlighted formula here to this one here, the only difference is that we've inserted this multiplicative factor of h of k omega naught. So in other words, to get from our starting point in this problem, which was this Fourier series, to our answer, which was this Fourier series, all we had to do was insert this factor here. In other words, multiply by a constant. And arguably this is much easier to do than convolution. Again, this helps to illustrate the power of eigenfunctions. Eigenfunctions can often be exploited to make problems much easier to solve. Earlier we saw that the information embodied by a function can be described in terms of its frequency spectrum. In particular, the frequency spectrum describes how the information in a function is distributed with respect to frequency. When working with systems, it's often beneficial to view the operations that systems perform as operations on frequency spectra. In other words, we view a system as being presented with an input that has some particular frequency spectrum, and then the system somehow modifies this spectrum in order to produce an output with a new frequency spectrum. For example, the system might amplify or attenuate certain frequency components in the input in order to produce its output. This process whereby a system modifies the frequency spectrum of a function is known as filtering, and a system that performs the filtering operation is called a filter. Now, there are many types of filters, but one important class of filters is a class of frequency selective filters. Frequency selective filters allow some frequencies to pass through with little or no distortion while significantly attenuating other frequencies. The three most basic types of frequency selective filters are low-pass, high-pass, and bandpass filters. And in the subsequent slides, we're going to look at each of these types of filters in more detail. The first type of frequency selective filter that I need to introduce is known as an ideal low-pass filter. An ideal low-pass filter eliminates all frequency components with a frequency whose magnitude is greater than some cutoff frequency, while leaving the remaining frequency components unaffected. And the frequency response of such a filter has the form shown in the middle of the slide. So in other words, it has this particular form here, where omega c is a constant that's referred to as the cutoff frequency of the filter. And the frequency response of this filter is shown plotted at the bottom of the slide. So the frequencies for which the frequency response is 1 correspond to frequencies that are allowed to pass through the filter without change and constitute what is called the pass band of the filter. And in this case, the pass band is going to be frequencies that are between minus omega c and plus omega c, in other words, frequencies in this range here. The frequencies for which the frequency response is 0 correspond to frequencies that are eliminated by the filter and constitute what is called the stop band of the filter. So the stop band of the filter would be frequencies that are greater than omega c, in other words, frequencies out here, and frequencies that are less than minus omega c, in other words, frequencies out here. And since this type of filter allows lower magnitude frequencies to pass through it, it's referred to as a low-pass filter. The next type of frequency selective filter that I need to introduce is known as an ideal high-pass filter. An ideal high-pass filter eliminates all frequency components with a frequency whose magnitude is less than some cutoff frequency, while leaving the remaining frequency components unaffected. The frequency response of such a filter has the form shown in the middle of the slide, in other words, this form here, where omega c is a constant that's referred to as the cutoff frequency of the filter. And the frequency response is shown plotted at the bottom of the slide for this type of filter. And the frequencies for which the frequency response is 1 correspond to frequencies that are allowed to pass through the filter without change and constitute what is called the pass band of the filter. So in this particular case, the pass band is going to be frequencies that are less than minus omega c, in other words, frequencies out here, or frequencies that are greater than omega c, in other words, frequencies out here. The frequencies for which the frequency response is 0 correspond to frequencies that are eliminated by the filter and constitute what is called the stop band of the filter. In other words, this is going to be frequencies that are between minus omega c and plus omega c. In other words, this range here is the stop band of the filter. Now, since this type of filter allows higher magnitude frequencies to pass through it, it's referred to as a high-pass filter. The next type of frequency selective filter that I need to introduce is known as an ideal bandpass filter. An ideal bandpass filter eliminates all frequency components with a frequency whose magnitude does not lie in a particular range, while leaving the remaining frequency components unaffected. The frequency response of such a filter has the form that's shown in the middle of the slide here, where the constants omega c1 and omega c2 are sometimes referred to as cutoff frequencies of the filter. And a plot of the frequency response is shown at the bottom of the slide. The frequencies for which the frequency response is 1 correspond to frequencies that are allowed to pass through the filter without change and constitute what is called the pass band of the filter. So in this case, this would correspond to frequencies in the range minus omega c2 to minus omega c1, in other words, frequencies in this range here, as well as frequencies between omega c1 and omega c2, in other words, frequencies in this range here. The frequencies for which the frequency response is 0 correspond to the frequencies that are eliminated by the filter and constitute what is called the stop band of the filter. So this would correspond to frequencies that are less than minus omega c2, in other words, these frequencies out here, frequencies between minus omega c1 and plus omega c1, in other words, frequencies in this range, and then frequencies that are greater than omega C2, frequencies in this range out here. Since this type of filter allows frequencies in a particular range or frequency band to pass through, this type of filter is referred to as a bandpass filter. At this point, I'd like to consider an example to further illustrate the concept of filtering, and in particular, I'd like to consider example 5.10. In this example, we're given an LTI system with input x, output y, and frequency response function h, where h is given by this particular formula here. And if we plot h has the form that's shown in this annotation that's been added to the example. From this graph, you can see that the system that we're dealing with would correspond to a low-pass filter. The reason why is the form of this frequency response here is the form that a low-pass filter frequency response would have. We're told that the input x for the system is given by this particular formula here. And then in this example, we're asked to do a number of things. In part A, we're asked to find the Fourier series representation of x. In part B, we're asked to use this representation in order to find the response y of the system to the input x. And then in part C of the question, we're asked to plot the frequency spectra of x and y. So again, in part A of the example, we're asked to find the Fourier series representation of x. And it's sort of implied in this particular example that we want the Fourier series representation expressed in exponential form. So before we start blindly plugging into the Fourier series analysis equation in order to compute Fourier series coefficients, it's good to stop and think about what we're actually doing here. The expression that we're given for x, in other words, this particular expression here, effectively already is a Fourier series, but it's a Fourier series expressed in trigonometric form. So it's actually relatively easy to convert this expression into a Fourier series in exponential form. And the way we do this is as follows. So we start out with our Fourier series expressed in trigonometric form, and then we can use Euler's relationship to take each one of the cosine terms and rewrite them as pairs of complex sinusoids. So by using Euler's relationship, we end up with this next line. Then we can simply reorder the terms and do some very basic algebraic manipulation to get to this line here. And then to find the Fourier series in exponential form, all we need to do is identify the fundamental frequency, which is denoted as omega naught in this problem, and we need to identify the individual Fourier series coefficient indexes, which are referred to as k in this particular problem. So for example, we need to take the exponentials, the constants that appear in the exponentials, like the 2 pi here, which is the product of k, the Fourier series coefficient index, and omega naught, the fundamental frequency of x, and we need to factor it into the k portion and the omega naught portion. And when we do this factorization, we have to do it such that the value that we claim to be k in each one of these terms that we end up with, the k value must be an integer, because by definition the Fourier series index has to be an integer. And also the value that we get for omega naught, it has to be the largest possible value that we could choose for omega naught. The reason why is that when a function is periodic, it's periodic with an infinite number of periods and an infinite number of frequencies. But the fundamental frequency is the largest of all the frequencies with which the particular function is periodic. So as it turns out, if we try to perform this factorization, the largest value that we can choose for omega naught, such that the k values that we get in all of the terms, so for example -3, -2, and so on, the largest value that we could choose for omega naught is 2 pi. If we choose any larger value, then some of the values that we get for k in these various terms here will not be integer, which we know clearly must be wrong, because the Fourier series coefficient index by definition is always an integer value. So from this we can infer that the fundamental frequency omega naught is equal to 2 pi, and then the Fourier series coefficient indexes for these terms correspond to -3 for the first term, -2 for the second term, -1 for the third term, and so on. So we can take these terms here and write a Fourier series in exponential form, in other words a Fourier series that looks like this, where the Fourier series coefficients are given by these, or given by this particular formula here, and again omega naught is equal to 2 pi. So this completes the first part of the problem, part A. We've now found the Fourier series representation of x expressed in exponential form. At this point, I'm just going to scroll the solution up so we can see the next part of the solution for part B. So recall that in part B of the problem, we're asked to find the output of the system, which is denoted by y, when the input to the system is the function x. And in order to do this, we're going to use eigenfunction properties of LTI systems. So in part A of the example, we found a Fourier series representation for the input to the system, in other words, the function x. So if we want to find the output of the system, we know due to eigenfunction properties of LTI systems, the output is going to be a Fourier series. And in particular, it's going to be almost the same Fourier series that we had for the input. The only difference is that the coefficients that appear in the Fourier series for the output of the system are going to be multiplied by the value h of k omega naught. So ak corresponded to the Fourier series coefficients for the input to the system, and to get the Fourier series coefficients for the output of the system, which are denoted by bk, we simply need to multiply by h of k omega naught. So we just need to take the function h and evaluate it at various different points. And if you recall from earlier, the function h is equal to 1 for omega between minus 3 pi and 3 pi, and it's 0 otherwise. So to try to make this computation a little bit more organized, what I've done is I've grouped the Fourier series coefficients that we're computing on the basis of whether or not the function h is equal to 1 or equal to 0 when we compute the function h. So in the first three cases, the cases of b0, b1, and b minus 1, it turns out that when we evaluate the function h, the value we get is 1. Because in each of these cases, here we're evaluating h at 0, here we're evaluating h at 2 pi, and here we're evaluating h at minus 2 pi. But all of these values lie in the range minus 3 pi to 3 pi, so the function h will be equal to 1. So in all of these three cases for b0, b1, and b minus 1, we get 1 for the function h, which means we're just multiplying by 1, which means that the Fourier series coefficients for the output will just be equal to their corresponding input Fourier series coefficients. Then the remaining four Fourier series coefficients, b2, b minus 2, b3, and b minus 3, these correspond to cases where the function h, when we evaluate it, is equal to 0. So here we're evaluating h at 4 pi, at minus 4 pi, at 6 pi, and minus 6 pi. And this is going to correspond to the otherwise case over here. In other words, all of these values of omega correspond to values that are not between minus 3 pi and 3 pi. Therefore, the function h is equal to 0. Therefore, we're multiplying by 0 in each of these four formulas here, which is going to give us 0 for the Fourier series coefficients b2, b minus 2, b3, and b minus 3. So we can combine all of these results together and just write them a little bit more concisely as is written on this line here. It turns out that all the Fourier series coefficients that are non-zero happen to be equal to 1, and there's 3 of them for Fourier series coefficient indexes k equal to minus 1, 0, and 1, and then all the remaining Fourier series coefficients are 0. So this completes part B of the problem, where we're asked to find the output of the system. The output of the system is given by this particular Fourier series, where the Fourier series coefficients bk are given by this formula here. So at this point, I'm just going to scroll the solution up so we can see the solution for the last part of the problem. In other words, the solution for part C. So recall that in part C of the example, we're asked to plot the frequency spectra of x and y. So we've already found the frequency spectra of x and y in earlier parts of the example, so we don't need to actually find these spectra at this particular point. We just need to plot them. So in part A of the example, we found the frequency spectrum of x, and in particular, this corresponded to the Fourier series coefficients that were denoted as ak. So here we've simply plotted the Fourier series coefficients ak. And we've also found the frequency spectra of y. In part B of the problem, we found the Fourier series coefficients for y, which were called bk. So we've simply plotted the Fourier series coefficients for y here. So this is the frequency spectrum for y. And in addition, on the first graph, I've superimposed the graph of the frequency response function as well, because this is helpful to visualize what the system's actually doing. Because this function h is always equal to either 0 or 1, in cases where it's 0, for example, at the frequency 6 pi, the function capital H is equal to 0, we're going to multiply this coefficient times 0, which gives us 0 for this coefficient down here. In cases where this function is equal to 1, for example at a frequency of 2 pi, we're going to take this coefficient value ak and multiply it by 1, which gives us the same coefficient value for the corresponding bk value. So in other words, in places where this frequency response function is 1, we're just copying Fourier series coefficients, or copying their values from the input spectrum to the output spectrum. In places where this function capital H is equal to 0, we're basically taking whatever coefficient was in the input and we're just setting it to 0. And then lastly, one final observation about this example. Notice that nowhere in our solution did we use convolution. And the reason for this, the reason we didn't need to use convolution, is we were using eigenfunctions and exploiting the properties of eigenfunctions of LTI systems in order to solve this problem in a way which didn't involve convolution. So again, this example helps to illustrate the power of eigenfunctions.